Dear students, welcome to the online class for the subject Power System Analysis and Stability. Today we are going to discuss the topic from unit number 5, Stability Studies. So what is mean by stability? So power system consists of lot of components like generator, motor, transformer, transmission line, etc. etc. In a power system, all components will be operating in parallel. So if any fault exists, any one of the generator or any one of the equipment is deviating from the synchronism, that is, if it is not parallel, then it will affect the other components and thereby affecting the whole network. So when we are considering 5 or 6 generators operating in parallel, and due to a fault, if any one of the generator loses or lost its synchronism, certainly it will affect the other generators. So because of this, the whole system will undergo deviating from the stability. So that's why we are going to study the stability part of the power system. With interconnected system, it is continuously growing in size. See, the power system, it is not stringent. So when the size of the area has been increased, then the power system has to be increased. So when interconnected system continuously growing in size, it is becoming increasingly more difficult to maintain synchronism between various parts of the power systems. So now we can discuss about the definition for stability. So it is the term applied to alternating current electrical power system denoting a condition in which various synchronous machines of the system remain in synchronism or in step with each other. So if it is deviating from the synchronism, then we will be calling it as out of step or deviating from the synchronism. So it is nothing but instability. It denotes a condition involving loss of synchronism or falling out of step. So the types of stability are, it has been classified into steady state and transient state stability. So in today's class, we will discuss about swing equation. So this is one of the method of improving the stability. So what is mean by swing equation? The behavior of a synchronous machine during transient period is described by the swing equation. So how the machine will behave if any fault occurs, any disturbance occurs, that is transient period. So we know that the torque exerted on a rotating body is given by the product of moment of inertia I. The unit is nothing but kilogram meter square, and angular acceleration alpha. So the torque is nothing but Ts equal to the product of I into alpha. The unit for alpha is nothing but radian per second square. Then now we are substituting the value of alpha here. So that is nothing but d square theta divided by dt square, because theta is nothing but angle. Angular acceleration, so theta is differentiating d theta by dt is nothing but angular velocity, and d square theta divided by dt square is nothing but angular acceleration. So where theta is the angular position of the rotor in radians at any instant of time, and t is time in seconds. So it is convenient to measure theta with respect to a reference axis that is rotating at synchronous speed. If delta is the angular displacement of the rotor in electrical degrees from the synchronously rotating reference axis, and omega s is the synchronous speed, that is 2 pi ns angular speed in electrical radians, then theta can be expressed as the sum of the equation 1, time varying angle omega st on the rotating reference axis, and equation number 2, the torque angle delta of the rotor with respect to the rotating reference axis. So in other words, if you are writing the equation for theta, that is angular velocity, so angle, theta is equal to omega st plus delta. The unit is electrical radians. So when we are differentiating the equation number 3 with respect to time, we are getting d theta by dt, then Omega is, when differentiating with respect to time, then t become 1 plus d delta divided by dt. So this we can represent it as equation number 4 for future calling. Then differentiating once again with respect to time, we are getting d square theta divided by dt square is equal to d square delta divided by dt square. So this d square theta divided by dt square is nothing but angular acceleration. So the angular acceleration of rotor alpha is equal to d square theta divided by dt square. This also can be equal to d square delta divided by dt square electrical radians. So in a synchronous generator, the accelerating torque, so torque has been represented as capital T. A is nothing but acceleration is equal to the difference of input shaft torque Ti and the output electromagnetic torque Tu. So Ti is nothing but shaft torque and Tu is nothing but output electromagnetic torque. This is input shaft torque, output electromagnetic torque. The difference between these two is nothing but accelerating torque. So now we are representing, so this TA is nothing but I into d square theta divided by dt square, right? So we have written already. So I into d square theta divided by dt square, we are substituting here. So instead of d square theta divided by dt square, it's also been equal to d square delta divided by dt square. That's why we are substituting d square delta divided by dt square instead of d square theta divided by dt square. Then this TA, accelerating torque, is equal to shaft input torque minus output electromagnetic torque is equal to I into d square delta divided by dt square. So upon multiplying both sides by angular velocity omega, we are getting omega TA is equal to omega Ti minus omega Tu I omega d square delta divided by dt square. So this omega TA is nothing but accelerating power, and this omega TA is nothing but mechanical power input, and omega Tu is nothing but electrical power output. So this we are replacing this as omega TA is nothing but PA, omega Ti is nothing but Pi, and omega Tu is nothing but Pu. This is accelerating power, then mechanical input power, electrical output power, that is equal to I omega d square delta divided by dt square. Also, since angular momentum m is equal to I into omega, that is moment of inertia into angular velocity. So equation 9 can be written as P is equal to Pi minus Pu, that is equal to m into d square delta divided by dt square. So this equation 10 is called as a swing equation. So it is a non-linear differential equation of the second order. Thank you. And if you look into the shape of the swing curve, the solution of swing curve gives the variation of delta C. It may be asked in 1 mark. The solution of swing equation gives the variation of delta, that is in electrical radians, with respect to time in seconds. Once we are drawing the curve between delta and t, that is nothing but swing curve. The graph when plotted is called as a swing curve. It provides information regarding stability. If delta increases continuously with time, the system is unstable, while if delta starts decreasing after reaching a maximum value, it is inferred that the system will remain stable. See, once it reaches the maximum peak and it is deteriorating, it is decreasing, then it will become a stable stage. So where we are using the swing curve? Swing curves are useful in determining the adequacy of relay protection on power systems with regard to the clearing of faults before one or more machines become unstable and fall out of synchronism. The critical clearing time can be determined to specify the correct speed of the circuit breaker to make the system stable. So to plot the swing curve, the swing equation is to be solved. It can be solved by step-by-step method, Euler's modified method and Runge-Kutta method. At present, digital computer is used for solving the swing equation. Thank you.